I want to do, this is too big. Trying to move somewhere. I don't know if y'all can see that arrow. Yeah, there we go. There, a little bit more. Hold on, I moved too much. There it is, right there. Okay. Can y'all see that black dot? Do you see the vector that goes with it? Yes? I want to show you that black dot on the surface. It's right, man, it's hard to see that. It's right here, right? It's hard to see that this is, if I were to go this way, I'd start falling down into that little cavern, right? That little crevice, and I'd start rolling off. So what's happening right now is if I were to place a ball here on this surface, it would want to roll that way. Do y'all see that? The gradient vector is always pointed in the direction of maximum ascent, or greatest rate of change. The negative of the gradient vector would be the one that takes you down the other way, right? So you just multiply this vector by -1, and that would point you in the opposite direction. So what would happen if I move this ball down here and put it right here? The gradient vector should still point, back towards the center, but very long vector, right? Because it's steeper there. And I want you to see if I move this is that crevice. Is that the right word? I shouldn't use crevice. Let me move it back there. See, I'm rolling it down that hill. And do you see how long the vector got? It went off the screen. So I've rolled that. Man, it's really a bad picture. I've put it back here, and now it wants to roll down there, so the steepest descent is over here. You're kind of seeing the relationship between the gradient vector field and the surface, right? Okay, conservative vector fields. So all we know right now is that if somebody gives us a scalar function, right, a scalar function, f of x, y, or f of x, y, z, we can take the gradient of it, and that creates a gradient vector field. Now we're talking about something different. Conservative vector fields. So any vector field, capital F, is called conservative if there's some scalar function, little f, such that that vector field is just a gradient of f. This just means the vector function is the gradient vector field of some function. Okay, what? What the hell are you talking about? What I'm talking about is this. The problem we just did before this, right? I gave you a scalar function, right? Let me put it up here again. It was, scalar function was x squared y minus y cubed. It was x squared y minus y cubed, right? Then I asked us to find the gradient vector field. The gradient vector field was just 2xy, comma, x squared minus 3y squared. That was the gradient vector field, right? What this note says is this. It's saying if somebody hands you a vector field. So what if I came in here and said, hey, everyone, look at this vector field. And I gave you this vector field right here. Okay? And I said to you, hey, everyone, is this conservative? You would say what? Is this a conservative vector field? Yeah. Yes. Why is it conservative? Because where does it come from? It comes from the gradient of some scalar function, right? If a vector field is the gradient of some scalar function, then it is called conservative. That's just the definition. The challenge would be, had I not given you this, right? Had I not given you this, and I just started the whole conversation with this and said, hey, is that conservative? Then what would you have to do to answer yes? You would have to find the little f that creates that when you take the gradient, right? You'd have to find that little f. And it's possible to do. It is possible to do. But this, for now, is just a definition. And we're gonna use it again, so please just, put it in there because we'll need it. When I say conservative, that means it's the gradient of some scalar function. Wondering if we should try. No? Try? No? Let's move on. That's it. This section is just introduction. Vector fields. Yes?
But we could find it, right?
You could, and we will.
Okay.
But we're going to do it with more complicated ones. This one, we're going to do integration.
Yeah.
We're going to do integration to do it. But we're going to have to do what's called partial integration. So, and it gets, it's like a partial. When you integrate with respect to a certain variable, but then the others you have to hold as constants. But we just have to keep track of a few things, but we'll be able to do it. All right, that's it. Introduction. Now, 13.2. Wow. 13.2 formula summary. So I have an entire document that is just the formulas from 13.2. This is just the 13.2 formulas. So this is a pretty heavy section, would you say? Just from the look of that? All right. I think this is it. This is where it begins. Like this is where the chapter 13 we start to really get into it. All right, line integrals. Ever heard of a line integral before? No? Line integral? Well, they have a terrible name because you would think that they involve lines. They actually involve curves. So I put curve integral here. But what the hell is a line integral? So first thing, suppose we have a function f of xy. Okay, what is f of xy? Some surface, right? Say we have a surface. And then what we're going to do is we're going to define that surface on a curve in C. That means we're going to restrict that surface to a curve. Here's the picture. So here's a surface, right? There's a surface. But I don't want you to look at the whole surface. I just want you to look at the surface if you plug these points, see that down here in the domain? If you just plug those points that are on this semicircle into the surface, you would get that blue up there, wouldn't you? Okay? So we've got a surface. We are restricting that surface to a curve. And now the question is this. What would this be if we took a curtain and dropped it down from that curve to the ground? What's the area of that curtain? Okay? What's the area of that curtain? Is the question. Now, you might be like, who cares, right? But this could be tied into some things later, like, let's say that this red curve is actually like a metal bar, and then this function is the density at each point, right? Then this integral would give you, we could use this integral to figure out what the mass of this is. We could find the center of mass. We could find the moments of inertia, all that stuff. Okay, so there's a value to this, is what I'm getting at. But geometrically, does it seem reasonable that we should be able to do this? Find the area? So this is no longer a volume, is it? It's not a volume, it's an area. So what we're going to do is we're going to go back to Cal 2. When we were in Cal 2, right, how do we find the areas? What was the geometry behind this? We cut this into a bunch of rectangles, right? And we said, okay, for each rectangle that we cut, the height of this was just the function's value. And then the width of this we called dx, or change in x. And so the area of one of those was just these two multiplied, f of x dx. And that gives you the area of one, right? And then we use the integral to add them all up. That's what Cal 2 is about. We want to do the same thing here, right? We want to do the same thing. But the difference is, what is the difference? There's a big difference between the curtain that I just showed you and this curtain. This curtain is what? The line. The line, right? It's straight down here. What's ours? It's curved, right? We have to account for that. How do we account for that? This is no longer dx, is it? It's what? It's part of the curve, right? So what would be the best thing we could use to do that? I think I have a picture here. Here's the picture. If I take one rectangle in here, I know the height of it. What's the height of this piece? It's the function, it's the surface, right? So the height of this should be the function evaluated at some point in this domain, but then how wide is it? Not dx, not dy. D, what do you mean A? I'm not sure. I mean, I don't want to say no to A, but...
Well, it's the dx and dy multiplied together, right?
Kind of. Let me do it this way. Let me do it this way. Can we look at that little red piece, or not the red piece, the little purple piece that I just drew? Can we draw that over here? This little purple piece? And then notice my x-axis goes this way, my y-axis goes that way, right? So we got this little arc, like this. Arc, I'm almost giving it away. Right? If this right here is dx, and this right here is dy, right? Right triangle would give us an approximation, wouldn't it? So we could do something like dx squared plus dy squared equals that thing squared. And if you go back to Cal 2, this is exactly how we defined arc length. We just went through and we just used Pythagorean. So instead of dx, we're going to call that thing ds, little s. That right there, this right here is ds. Now what is ds? Just like I said here, it's these two things, square root of those things squared and added together, right? Pythagorean. So it just comes off this picture. Y'all see that? Pretty freaking cool. It's arc length, right? So if somebody gives you a surface and they restrict it to a curve, and then we want to drop a curtain down and find the area, what we're going to do is we're going to find the area of all those little rectangles, which are the height of the function, the surface, times the width of the little rectangle, which is the arc length little piece, ds. We add all those up with an integral. What are we integrating over? The curve C that's on the ground. Right? That's your bound. That's your curve on the ground. So this is called a line integral with respect to, so think about what we had respect to. We've had with respect to area, with respect to volume, right? What is that ds to us? S is really a what? An arc length, right? So we say this is with respect to arc length. Do I say it up here? I will at some point. Okay, so we take our function, we evaluate it, and then we have to calculate this. Now, there's a problem. How do we define the curve that's on the ground? To define the curve, we need to draw it with parametric equations. So way back in the beginning of chapter 10, when we talked about vector equations, we said we could draw curves, can't we? In 2- and 3-dimensional space. Well, guess what? To do this integral, we have to find a parametrization of this curve. We have to be able to draw it. That way we can plug that parametrization into the function and then take the partial derivatives, or the derivatives of that curve. So there's a little bit more, I mean the formula, you tell me, does the formula make sense geometrically from what I showed you? That's the height of the rectangle, that's the width of the rectangle. The problem is figuring out the height based on the curve and figuring out the arc length based on the curve. So this is basically our formula, our first real formula for this section. The line integral over that curve C with respect to arc length is this, so long as we have found parametric representations of the curve. So we can draw that curve using the parameter t, and t is going to be restricted between two constants, a and b. How are we doing? 20 minutes. Okay. I'll put that back up there if we need it. First example. We would like to find the line integral over that curve C of 2 plus x squared plus y squared. Why don't we take a look at that surface? Yeah or no? Yeah? This is our f of xy, right? With respect to arc length. C is the upper half of the unit circle. Let's take a look. Shit, where is it? I don't have it? Where is it? I don't have the picture? I wonder if I deleted it. Let me reevaluate this. Sometimes I accidentally delete things. Oh, you know what? I do have it. It's this problem right here. Sorry, I forgot. It's this. It's the first thing I showed you. It's that, okay? So that's what we want. We want to evaluate this surface, right? We want to move along the upper half of the unit circle, right? We want to drop a curtain down and find the area. So the first thing I'm going to do is try and figure out if I can find a parametric representation of the circle. C. So I need to draw this, right? Unit circle, I need to draw this. Goes from there to there. This is C right there. Well, I know how to do that, I think, right? This is going to be, how do we draw circles? Cosine and sine, right? Okay, so the x, I'm going to call that cosine t. The y, sine t. And to draw just that top half, my t needs to be between 0 and pi. I have these panic attacks sometimes where I feel like this is... I don't have panic attacks, but yeah, that's all right. I had another class and I recorded everything. I had it on mute the whole time. I'm sure I've done it in here too, maybe. No, not yet. All right, so there's my parametric equations that draw that curve, right? That's it. So now what I need is the actual formula for this. Let me write the integral down here. I'm doing the line integral over C of 2 plus x squared y ds. Using this formula, this will be equal to, all right, first thing we have to do is we have to see, do we have limits of integration? Our limits of integration are going to be the restriction on t, which for us is between 0 to pi, right? 0 to pi. And now it's the actual surface, right? This thing right here, but you've got to replace all your x's with your parameterization of x, all your y's with your parameterization of y. So instead of this, I have 2 plus, what's x squared for us? Cosine squared, t, and then instead of y, sine t. Okay? We okay? Now, the square root of times the square root of, we need derivatives, right? We need derivatives. So let me do this part and this part. Let me do that over here on the side. What is dx dt? Derivative of x with respect to t is? Yeah, negative sine t. I'm gonna move this stuff out of the way. I don't think we need that. It's just getting in my way there. Okay, so we need the derivative of this, right, with respect to t. So negative sine t. And then we need derivative of y with respect to t as well, right? So that's going to be cosine t. Oh, cosine t. Getting ahead of myself there. So now I want to take the derivative of x with respect to t and square it. So take that and square it. Negative sine t, but then square it, plus that one squared, and square it, and then d what? T, dt. So please understand, everyone, that this right here, oh, come on. This right here is what ds is. That is your arc length formula from Cal 2. Normally in Cal 2 we don't have parametric equations, unless you did cover parametric. I know in my class we don't get to that, but this is basically the same idea, square root, and then you have derivatives squared. Good news, right? Good news, sine squared t plus cosine squared t is 1, square root of 1, 1. Yes,
So, just a quick question.
Yep.
That square root of your
Yes.
partial,
Yep.
right? Is that the Jacobian determinant for an arc?
It's, no, because we're not doing a change of variables. We're not changing variables over to different.
I thought we did from x to t.
Okay. Let me try and rephrase this. Your Jacobian, right? You're switching from, what does your Jacobian become if you go from one variable to another variable? Like, see, the Jacobian comes from the idea of the determinant, right, of a matrix.
Yeah.
A 2 by 2 matrix. What's a determinant of a 1 by 1 matrix? See, because we're going from this to one thing, right? Like one. We're not going from u to x. I'm sorry, not from x to u and y to v. We're going from x to a function of t and y to a function of t. So we're going to one thing instead of two different.
Yeah. Okay.
So what's a determinant of a 1 by 1? Right?
Yeah.
What do you think it would be?
I don't know.
Well, think about it. I mean, if you have A, B, C, D, right? You want this determinant, right? You do that times that minus. But what if your matrix is just one thing? It's just that, right?
Yeah.
So
It would be a complete translation.
yeah, you're not going to have to factor that in.
Okay.
I think the thing that's being kind of lost in this is that we're not changing. Our curve is not like moving from this curve in this space to another curve in another space.
Oh, okay.
Right?
Yeah.
All we're doing is we're changing the way we draw this and getting in terms of a single parameter, as opposed to trying to look at this as like y is a function of x. We're saying x is a function of t and y is a function of t.
Okay.
So we don't have the Jacobian to really deal with here.
Okay.
It's a good question,
Yeah.
but it's not factoring into this at all. I'll try and get a better answer if I can think of a better way of saying that. I'll say something else. All right, can we handle this though?
Yeah.
Yep, this is just one, and then that integral. Yeah, well, you actually don't need to do power reducing because that's where we are, right? Just this?
0 to pi.
0 to pi, yeah. Why'd I put 2 pi? Because these you can do individually, right?
Yeah.
So the antiderivative of 2 is 2t, and then here I'll put a plus, but let's think about this. For these two together, you can do basic u sub.
Yeah.
If u is cosine, then that's the derivative of cosine, but you're off by a sign, and then you'll have to scale. And so I think it'll be negative 1/3 cosine cubed t. We can check this. Take derivative real quick. 3 comes out, kills off. You get negative cosine squared. Then derivative of cosine is negative sine, so then it becomes positive. So that should be the antiderivative of this piece, just with the u sub. And so that's my antiderivative, right? 0 to pi. And then you plug in and get your answer. And that'll be the area. Okay? All right. The challenge of these problems are going to be coming up with the parametrization and making sure you have that right. Okay, we're about to maybe set up the next example. We won't get too much into it. This says that if you have one curve that is made up of a bunch of other curves, that if you want to do the line integral, then you can do them separately and add the answers together, which should make sense to you. Like, it's like if you're trying to find the surface area of one big curtain, you can split it up into a bunch of smaller curtains and find the area of each one. Oh, God. Don't use purple. So here's an example. I'll come back to the problem, but here we have a surface. The surface is very nice. It's a plane, right? You'll see that plane. And the ground is actually a combination of two things. It looks kind of like a parabola and then a straight line segment. And so if we want to find the area underneath this whole thing, right, dropping it down, just that area, then what we can do is we can go just along the parabola first, figure out that area, and then move just along the line and figure out that area and add the two together. So, yeah. I think I want to stop here. We don't have enough time to do this problem, but I want us to go back for a second real quick. I want us to go back to Cal 2, just for a second. If I were to ask you to do this in Cal 2, what we're doing here is looking at this parabola between 0 and 4, right? Like that. And you're trying to find this area. That's what we do in Cal 2. So can you see that as an area of a curtain? Can you? Like, can you take this off the sheet of paper? Can you take this off the sheet of paper right now and see a surface and a curtain being dropped? Let me see if I can do it over here. So if this is your x-axis and this is your y-axis and this is your z, then isn't our surface just a folded sheet of paper like this that's going like that, right? So that would be a paraboloid like this. I'll bring it out here. It's like this. And it goes through like that. Something like this. Okay. Like that. Okay. And so where that thing intersects the xy plane, right here, we want just that area underneath here. So what we need to do is draw a little line segment that comes out between 0 and 4. That's our curve on the ground. This is our curve on the ground. And now if you look at those points plugged into the parabola, you get this thing right there. And if you drop down, we're trying to find that area right there. So everything we did in Cal 2 is actually just a specific case of this. Let's see if we can continue. Can you tell me what that surface is? It's a function of two variables. X squared. That's it. Because y is free, right? Y is free, so the y moves it up and down, or down the y-axis, right? So that's your function of two variables. Can you define that curve for me? This is the part we're going to need to do next class. Can you define that curve right here? C. Well, what is it? In three-dimensional space here, right? That curve from here to here, 0 to 4. Isn't that just a line segment? A line segment. How do we draw lines in here?
Just the constant number, whatever it is.
Yes, go back to vector functions. Remember how we did lines? R of t equals R naught plus TV. Remember this whole thing? Okay, can you give me an R naught off that thing? 0 has to be two-dimensional. Because this is 0, 0? Okay, 0, 0. Plus t times, can you give me the direction vector? That's the vector that goes from here to here. 4, 0. And then put these together and you just get the vector 4t, what? 0. And now this is your parametric. Your x is 4t and your y is 0. And now let's use the formula I just gave you. Okay, if we want to do the line integral, right? The line integral of this over c of x squared, we do that, right? But we have to replace x with what? 4t squared, and then square root of dx dt. 4 squared plus dy dt, 0 squared dt, like that. Pardon? Yeah, that'd just be 4. Oh, I forgot to put, what are our limits of, what are our limits? What's our restriction on t here? 0 to 1, because remember, when we do a line segment, if we want to start here and end here, we always go 0 to 1. So this integral will go from 0 to 1. So that's just 4, right? And then this 4 squared is 16. 16 times 4? 64 integral from 0 to 1 of t squared is what we're doing, which is dt. And then 1/3. So 64 thirds t cubed, evaluated 0 to 1. I know I'm squeezing this in here, sorry. 64 thirds should be our answer. Now let's do it the Cal 2 way. The answer was 1/3 x cubed, 0 to 4. And you get 64 thirds. So the point is that line integrals, right, that we're doing now are an extension of what you did in Cal 2. Every integral you ever did in Cal 2 for area under curve was really just a line integral along a line segment on the x-axis, which meant that when you draw that line segment with your parametric, this will always be 0, right? And then that part will always turn out to be a constant. And okay, I'm digressing. We'll have to pick up right here next time, all right? Just homework-wise, just try and finish up chapter 12. And if you want, you can look at 13.1. There's some stuff in 13.1 you can mess with. Don't get too bogged down on 13.1. All right, everyone, have a great, week? No, is it? Shit, man. Just cranking away. Thanksgiving break. For this class, there's not a day off. Yeah, we're here on Wednesday. Yeah, not my choice. I mean, I understand students